No, 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 no. 5 to 6, yes, this is. And what about 6 to 1? No, 6 to only. We mentioned that 6 to 2 only. Okay. 1, 0, 0, 0, and 0. This is adjacency matrix for this graph. We define two matrices for the graph. The first is integrity matrix. The second is adjacency matrix. Okay. After that, we want to another this is integrity. The second one, A, is adjacency. Let me define another matrix as a Laplacian matrix D minus A. We define D minus A as a third matrix that we define for the graph. This tree matrix is very important to said anything about the matrices. If you have any question, do you have oh, okay. Okay, let me to continue. We define the first D matrix, the second A matrix, integrity matrix, adjacency matrix, and this third one is Laplacian matrix. Another important thing about the matrix is spanning tree. Let me erase this matrix to describe the spanning tree for this if you want to describe adjacency spanning tree for the system, we should define a tree in this graph that span all the nodes. We have 1 node, 2, 3, 4, 5, and 6. A tree should contain all these nodes and connect these nodes together. We can use it later. For example, I define this, 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 and this. I define the nodes like this. Okay? Or you can select the node like this, the bold one, the bold line. It's your favorite to select your tree based on your favorite, and it's not necessary that two person has selected one unique tree. The spanning tree is not unique for a graph. Okay, we define this. For example, we write the adjacency matrix for the above graph like this. I explain it for you. The integrate matrix is like this, and L is equals to D minus A. We define A and D. After that, you can obtain the Laplacian matrix. The Laplacian matrix has some properties. In all of the rows, the sum in all rows, for example, 1 minus 1 equal to 0, minus 1 plus 2 minus 1 equal to 0, minus 1 minus 1 2, 0, minus 1 plus 1 0, minus 1 plus 1 0, minus 1 minus 1 plus 2 are equal to 0. The row sum of the L are all 0. This is a very important properties for the Laplacian matrix. In next step, we want to discuss about eigenvalue of this matrix. The eigenvalue of this matrix, how we can define the eigenvalue? Lambda I minus L equal to 0. For example, for this matrix, the dimension of this matrix is 6 multiplied 6. Consequently, we have 6 eigenvalue. Lambda 2, lambda 3, lambda 4, lambda 6, lambda 5, lambda 6. We have 6 eigenvalues or eigen structure. Do you have any question? Do you hear my voice? Miss Rakat said that there is no voice. Do you hear my voice? Oh, yes. Ms. Rakat, I think you should check your speaker. Okay. Uh, okay. Do you have any question about this? Do you have any question? Thank you. Let me continue. Um, in There is a note here. Note that the row sum of L are all 0. How we can write this? Let me define this vector like this: 1, 1, 2, 3, 4, 5, 6, like this. L multiplied by vector 1 is equal to 0. Let me erase this matrix to show you. I want to show you this property. Okay. I multiply this matrix by 1, 2, 3, 4, 5, 6. Okay. Sorry. 1 multiplied by 1 is 1, 0, 1, minus 1. Minus 1 plus 2 minus 1, and so on. This is equal to 0, 0, 0, 0, 0. This means that this is L multiplied by vector 1 equal to vector 0. We should write this note. This note is very important. L multiplied by 1 equal to 0. Okay? And what about the eigenvalue of the system? I want to delete this term, and let me to describe or review this graph. This is undirected graph. There is no arc and there is no arrow in this graph. We call it as undirected graph. There is some arrow. We call it as directed graph, and without any, we call it undirected graph. If all the nodes in the graph are connected, we call it complete graph. Okay? For directed graph, for example, one in this graph can send data to all the nodes. For example, one can send data to 4 by 2. One can send data to 3. One can send data to 5 by 3. One can send data to 6 by 3. These nodes are follower, and one is the leader. Okay? One leader and the other is follower. And We call it this like directed star. This is like star. One is leader and the other are followers. This is undirected star. One is leader and the other are follower. Okay. Um, Consider the example mentioned in 2.2. This example. Sorry. I'm looking for the example. Example 2. Example. This is this example. Okay. For this example, for A, for this graph, the eigenvalue of the system are 0, 0.7, 1, and 2 imaginary eigenvalue, and the third one is 2.7. For the second one, this undirected graph, the first one is 0, the second one is 1.3, third 1.6, 3.6, 4, and 5.3. For the complete graph, for this graph, the eigenvalue of Laplacian matrix is 0, 6, 6, 6, 6, and 6. For directed tree, number D, like this, is 1, 0, 1, 1, 1, 1, and we can see all this graph has at least one zero eigenvalue. If you write A matrix for all of this, and consequently D, we can define L D minus A. The eigenvalue of D is equal to the eigenvalues of L are equal to this. The first one is 0, and the second one can be not selected as 0. Okay? If you obtain the eigenvalue of the L matrix, the first one always is 0. Okay? This is the eigenvalue of the system. There are some note. The Laplacian matrix has a row sum equal to 0. This means L multiply the 1 are equal to 0. And this causes all the graph have the first eigenvalue at 0. I show you in this table that the first eigenvalue are equal to 0. Okay? For undirected graph, the matrix of L is symmetric, and their graph eigenvalue of real. Let me come back to the table. This is undirected. This is undirected. Okay? C is undirected. Okay? E undirected. G undirected. and I undirected. All the undirected tree has real eigenvalue, but the directed graph may have uh, imaginary eigenvalue. For example, A is directed graph to imaginary. This is directed graph doesn't have any uh, imaginary. This directed graph has a 4 imaginary and so on. Okay? The imaginary, if you have a directed graph, the eigenvalue or all are real. But in undirected graph, maybe you have imaginary eigenvalue. But in undirected graph, if you have an undirected graph, L equal to L transpose. The matrix is symmetric. Okay? Why? Because A is symmetric. L equal to D minus A. D is diagonal. A is symmetric. This means L is symmetric. Okay? If you have a fully connected graph, for example, only sorry. If you have a complete graphs or fully connected graphs with n nodes, we have a S minus n eigenvalue, non-zero eigenvalues. Okay? Directed tree have all non-zero eigenvalue at 1. For example, like this directed tree, number D, the eigenvalues are all 1. This directed tree, eigenvalue are 1. Okay? A directed star is a directed tree, so all non-zero eigenvalue are equal to 1. Directed cycle graphs of lengths of n have n eigenvalue uniformly spread around the circle. Like this, number G. You can select, it is a loop. We start from here and come back to these nodes. And this means that, oh, sorry. In imaginary, the eigenvalue of the system, only the non-zero eigenvalue of the system, this now can be on the circle. Okay. And there is a Fiedler eigenvalue. In this table, the first eigenvalue. Sorry, I have a problem with my. Sorry, I have a problem with my pen, and this caused some problem for me. The first eigenvalue in this system, in this graph, are all equal to 0. We call the second eigenvalue as a Fiedler eigenvalue. If the distance between two, for example, distance between the 0 and the 0.7 equal to 0.7. The distance between 2 is 1.3. The distance between 2 are 6. 1, 1, 1, 1. The distance is 1, and the 0 and 0.2. Okay. The second eigenvalue are Fiedler. And when the second eigenvalue, the distance between the first eigenvalue that is equal to 0 and the second one that is lambda 2, if the distance is become big, this means that the consensus of the system, the consensus is very hard, because the topology of this graph may challenge us, and it's not good. And this distance, or the norm of the second eigenvalue as a Fiedler eigenvalue, is very important in connectivity. If this is big, if lambda 2 is big, this means connectivity has some problem. Okay. Let me start with consensus in scalar system. Let me unshare the document and share the whiteboard to write anything about consensus. Consider for example this multi-agent systems. There are some graph, okay? This is the graph of the system. For example, x1 equal to u1, this is the dynamic of the first agent. x2 dot equal to u dot u2, x3 dot equal to u3, x dot 4 equal to u4. Consider this multi-agent system. Combination of the graph. Let me change the color of the pen. Okay, this is dynamic of the, let me write, dynamics of agents. Okay, this is graph of connection. In large scale system and multi-agent system, there is two things in describing the system. One, the graph of the connection. Two, the dynamic of the graph. For example, agent 1 is a robot, agent 2 is a robot, agent 3 is a robot, agent 4 is a robot. Okay, the robot 1, the first robot is connected to second robot. The first robot is not connected to third robot. First robot is connected to fourth robot. The second robot is connected to first and third robot. The third robot is connected to second and fourth robots. Okay, this is all about the connection, but the dynamic of the robots, the first robot is like this: x1 dot, for example, x1 equal to Pn Q, P1 Q1. This is y and x. Okay, the location of the robots, the first robot is x1. Okay, we can apply the control input to this robot to change the location, for example, become here. Okay, this is all about the dynamic of the multi-agent system. I think let me have a break about 10 minutes. After 10 minutes we start the lesson again. Okay, have a break for 10 minutes. Okay, thank you. In this step, we know that for multi-agent system, we have a one graph, okay, like this, and the dynamic of the graph like this. The second step, we want to combine the dynamical graph and the dynamic of the agent and the graph. Let me go to the second page. X index of x dot index of I equal to ui. I is the agent, the number of the agent. We define u of I like this: a j xj minus xi. Okay, what this means? This is the elements of a index of I and j are elements of the adjacency matrix. Okay, adjacency matrix is IJ. Okay, of neighbor of the xi. Okay, we substitute ui in this equation. X dot I equal to aij xj minus xi. aij xj on, this is on I, sorry, this on j, minus aij xi on j. Okay, x dot I equal to minus xi. This is summation on j. You can change the position of xi. aij on j plus aij multiplied by xj. What does it mean? It means ai1 x1 plus ai2 x2 plus a I n x n. Okay, let me change. What does it means? This means d1 or the integrity of the matrix, the graph for di, the integrity for nodes of I. Okay, x dot I equal to minus di xi, okay, plus a, I want to rewrite Mr. Elias, do you have any question? Please write in chat. Okay, please write your question in chat. I answer that. AI1, AI2, AIN, X1 through XN. Okay, we call this, we name this as X, X1 through XN. Okay, let me next page, write it in next page. X I equal to minus d I xi plus ai1 through ain multiplied by x. What is x? X is x1 through xn, the state of all agents. Okay, let me rewrite the dynamic as follows. x1 dot equal to minus d1 x1 plus a11 to a1n multiplied by x. x2 dot equal to, based on this equation, minus d2 x2 plus a2. We apply, for example, 1, 2, 3, 4, 5 till n for I. 2, 1, a 2n multiplied by x. xn dot equal to minus dn xn plus an 1 through an n multiplied by x. X equal to x1 through xn. X dot equal to x1 dot through x n. We can write minus d1 dn. This is 0, okay? Plus, oh, sorry, a11 through a1n, an1 through ann, okay? Multiply by x. Sorry, please write, Mr. Elias, please write your question in English. I don't understand, unfortunately, Arabic. And what is this based on our definition? This is D matrix. What is this? This is adjacency matrix, okay? X dot equal to minus dx plus ax. X dot equal to minus d minus a x. Okay. What does it mean? This is Laplacian matrix, okay? X dot equal to minus Lx. This is the dynamic the dynamic for this system. Based on this procedure, we combine the graph theory and dynamic like this. We select this control input, okay, for the system, and we consequently the closed loop system. The dynamic of the agents are xi dot equal to ui, okay? The graph, I don't write anything about graph. When we fed D, A, and L for graph, we can draw a graph, for example, like this, and draw the arcs and the nodes. Instead of this this may hard for us. We can write DA and L for the graph. It's easier when we set the D and A for the graph is, for example, when I say D is 2, 0, 0, 2, okay, and A is 1, 0, 1, 0, 1, 1, 0. Let me change this. For example, I write D is equal to 1, 0, 0, 1. A is equal to 0, 0, 1, 1, 0. This is the definition for the graph. And based on this definition, you can draw the graph. It's not necessary to draw the graph because in a complex system, drawing the graph is very hard. Only we set D and A for the graph. For next step, let me write an example. This is the graph. Okay? Directed graph. This is a directed graph, okay? The dynamic of the x dot 1 equal to u1, the dynamic of the x2 dot equal to u2, the dynamic of the x3 dot equal to u3, okay? In the first step, define u1, u2, and u3. In the second step, write a closed loop system. Okay? Closed loop system is x dot equal to minus L x. Okay? Right. You have 10 minutes to solve this problem based on everything that I said before. Okay? Right. I'm waiting for you. Do you solve the problem? In the first step, we should define u. Okay? u1. I should write it here. At first step, we should, D integrate zero, 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 zero. In degree for 1 is 0, in degree for 2 is 2, in degree for 3 is 1, okay? And what about A, matrix of adjacency? 1, 2, 3, 1, 2, 3. From 1 to 1, 0. From 1 to 2, 1. 1 to 3, 1. 1 to, sorry, 1 to, oh, sorry, oh my God. From 1 to 2, 1, 1. From 2 to 1, 0. 2 to 3, 0. 2, 3 to 1, 0. 3 to 2, 1. 3 to 3, 0. And what about the L? L equal to D minus A. 0, 0, 0, 0, 2, 1, 0, 0, 1, minus 0, 0, 0, 1, 0, 1, 1, 0, 0. That's equal to, let me write here, L equal to 0, 0, 0, minus 1, 2, minus 1, minus 1, 0, 0. The row summation is 0, 0, and, sorry, 0. Okay, this is the L. Okay, the next step, I should write the graph again. 3. Let me check it. 3, 2, 3, 2. Okay, this is the graph. We want to design U1. I said that U1 equal to A1 J xj minus x1 based on the formulation. Yes, I said that A1 2 x2 minus x1 plus A1 3 x3 minus x1. This is all about the first controller. The second controller is A2 1 x1 minus x2 plus A2 3 x3 minus x2. U3 equal to A3 1 x1 minus x3 plus A3 2 x2 minus x. And what about the adjacency matrix? This is the adjacency matrix. I should write it again. 0, 0, 0, 1. This is adjacency matrix that we drive it before. Okay, this is 1, 2, 3, 1, 2, 3. Based on this matrix, A1, 1, A1, 2, A1, 3, A2, 2, sorry, this is 1, A3, 2 equal to, so let me check the matrix. This is 0. A3 3 equal to 0. Okay. A1 2 equal to 0. A13 equal to 0, A21 equal to 1, A23 equal to 1, A31 equal to 1, A2 equal to 0. U1 equal to 0. Okay. U2 equal to x1 minus x2 plus x3 minus x2. This is x1 plus x3 minus 2 multiplied by x2. U3 equal to x1 minus x3. This means the closed loop system is x1 dot equal to 0, x, check it, x1 plus x3 minus 2 multiplied by x2, let me check it, 1 minus 3, x1 minus x3. This is the closed loop system. Okay, the compact form. The compact form x dot equal to x is 0, 0, 0, 1 minus 2, 0, 1, 0 minus 1. Okay, this is minus L. That's finished this example. Okay, consider this example 1, 2, 3, and 4. X dot I equal to UI. Solve the problem. First step, design controller. Second step, write D, L, and A. 3, write closed loop systems. Okay, write this problem and send me in the Telegram or email the solution. Write the solution and send me in Telegram and or email. Do you have any question about this example? Don't forget to solve this example and send it for me. Okay, let me continue. The lessons. Okay. Based on our design for this controller, the consensus occurs in mean value of the initial condition. What does it mean? For example, consider that we have a three agents. The initial condition for the first agent is 1. The initial condition for the second agent is 2, and the initial condition for the third agent is minus 10. Okay? This means the consensus occurs in mean value. X SS equal to 1 plus 2 minus 10 over 3 is, okay, this is, for example, if we draw the system, for example, x1 is here, x1 is here, x2 is here, and x3 is here. All the diagram reach to this value. What is this value? This value is minus 7 over 3. Okay, this means mean value consensus. Consider another dynamics like this. This is the dynamic of the robots. The robot has velocity and heading angle. The robot can change heading angle and velocity, two input of the system. We can define the consensus. For example, theta I dot equal to aij. This is the element of the adjacency matrix. Theta j minus theta I. Okay, and v dot equal to aij vj minus vi. This is not a simple example. I don't want to solve this problem because this problem is nonlinear and it's not important for us to solve the nonlinear problem. Okay, let me continue with the linear one. It's better for us to know everything about linear. The second step in our approach is consensus based on the leader. If we don't have any leader, for example, if we have a three agent x2 0 equal to 2 and x3 0 equal to 6. The mean value is equal to 1 plus 2 plus 6 over 3. This means 9 is 3. The final value of the system is 3. Okay? If we don't have a leader, this is leaderless. If we have a leader, for example, x4 0 equal to 6, all of this agent should follow and reach, let me change it, for example 10. All of these agents should follow the leader and should lead to or reach to 10. Okay? Leader is very important. In all category, it's important to leader. The first step is to define leader. After that, we define the controller to let the follower to follow the leader. Okay? Let me find an example for you to solve with later. Let me write an example for three. This is the fourth. One, the agent 1 is leader. Agent 2, 3, and 4 are followers. Okay? I want, and the dynamic of the agent is UI. Okay? The difference between this problem with the previous one, in this problem we add leader consensus. I want to design controller for this system. UI equal to, we should define the consensus A, I, J, xj minus xi. This is like the previous one, plus x liter, let me write it, x liter minus x I. Okay, we add this term and we multiply this term like bi. This term is for consensus. This term is for leader tracking. Okay. Sorry. Sorry, I have a problem with this. Pen. We write U1 is leader. We don't have anyone about the first one. The second one, A 2j xj minus x2 plus b2 x liter minus x2. U3 like this, A 3j xj minus x3 plus b3 xl minus x3. U4 A4 sorry, j xj minus x4, b4 x liter minus x4. You can select a constant value for b2, b3 and b4 to design a trade-off between consensus and leader tracking. Let me solve one problem. I have a one leader, these two agents. Okay. This is the graph. The agent of the system is UI and agent of the leader is, for example, this. Solve this problem, design controller and a closed loop system for the system, and after that I ask one of the students to describe this problem for us. You have a 10 minutes time to solve this problem. No, 3 is not a leader. L is leader, 1 and 2 are follower. To simplify the problem, let me define U minus L1 equal to UL. Okay, nobody is volunteer for solving this problem. I solve it for you. In the first step, we should write an A matrix. Okay. How many agents do we have? Three agents with a leader. We can say that we have a 2 agents or 3 agents with leader. We call the agent as 0, 1, 2, 0, 1, 2. Okay, 0, this is a 0. 0 to 1, yeah, 1, 0 to 2, 1, 1 to 0, 1, 2, 0, 0, 1 to 2, 0, 2 to 0, 2 to 1, 1. This is A. And what about D? Mrs. Ilov, A is why? Why you write A like this? Miss Ilov, I think that you should check because this is from 2. From 0 to 0 is 0. 0 to 1, 0 to 1 is 1. I think you have a problem with A matrix. And what about D? D is in degree for leader is 0, in degree for 1 is 2, in degree for 2 is 1. And what about L? D minus A. 0, 0, 0, minus 1, 2, minus 1, minus 1, 0, 1. Okay, this is L. I should write again. I think this is okay, this is correct. And what about U1? I want to write U1. U1 is A I J X J minus X1 plus B1 X leader minus X1. Okay, we have it one agent. This is 1. A1 2 X2 minus X1 plus B1 XL minus 1. What about A12? A12, A12 equal to 0. This is 0. And U1 equal to B x liter minus x1. U2, A21 x1 minus x2 plus B2 x liter x2. And what about A21? A21 equal to 1. U2 equal to x1 minus x2 plus B2 xl minus x2. For simplicity, I write B1 as 1 and B2 as 1. This is x liter minus x1. This is x1 plus xl minus 2 times of x2. X equal to, x liter minus x1, x2 dots equal to x liter plus x1 minus 2 times of x2. X liter dot equal to minus x liter. Okay, x dot equal to, let me define x like this: x liter, x1, x2. X liter equal to x. This is minus 1, 0, 0. x1 equal to 1, minus 1, 0. 1, 1, minus 2. This is the closed loop system. Example, this is the first controller. U1 is XL minus X1. The second controller is XL plus X1 minus 2 times of X2. I want to draw the figure to describe this. For example, the leader XL equal to minus XL, okay? X dot 1 equal to minus X plus XL minus X1, and X dot 2 minus plus XL minus X minus X 2 times of X2. This is U1, this is U2, this is UL, okay? I write it like this: 1s x liter, this is x dot liter, okay? Or we can write UL, integral of UL, I write it here. XL equal to integral of UL like this, okay? Integral of u1 is x1. Integral of u2 is x2. Okay, what is ul? ul is minus xl. Okay, what about u1? u1 is xl minus x1. What about u2? Let me change the color. u2 is x liter. This is x liter. Okay, plus x1 plus minus 2 times of, or we can write plus minus. This is the multi-agent system. Okay, this is controller. Let me change the and this is multi-agent system. Really, the multi-agent system is very easy to design controller. Really easy. Let me to finish this lesson and continue on Thursday at 8:30. The LargeScale system to finish it and solve some problem for you. If you have any question, you can ask in Telegram group and I solve it for you. In Thursday, I try to solve one multi-agent system in MATLAB to show you the consensus and leader-follower tracking. If you don't have any question, let me to finish the class. Do you have any question? Have a good day. Goodbye.